So hopefully it is visible, right?
Yes, sir.
Okay. So we talked about conflict serializability and we said that that is a desirable, a concurrent schedule, if we can ensure that this is through a series of non-conflicting swap. If it can be converted into a serial schedule, then we say that this is conflict serializable, and that kind of concurrent schedule is acceptable. So in order to check, we talked about that given the particular schedule, we can form a precedence graph where every participating transactions will be a node.
Sir,
Yes,
sir, slide দেখা যাচ্ছে না।
just a minute. Why is it so?
স্যার প্রেজেন্টেশন নেই মনে হয় আপনার।
That was done. Okay, doing again. Is it visible now?
হ্যাঁ স্যার এখন আসছে, হ্যাঁ এসে গেছে।
Okay. Oh, possibly ওইখানটা হাইড করতে গিয়ে আমার স্টপ ওখানটায় প্রেস হয়ে গেছিল। Anyway, so as we are discussing that we can form the precedence graph where every participating transaction in the schedule is a node. We can have an edge like this. It shows that T1 is doing some operation in a different word, if I put it. T1 is doing some operation on a data item on which T2 will also do some operation, but those are conflicting. So that means in a serial schedule, equivalent serial schedule, T1 must precede T2. So that is the interpretation of this kind of edge. So if we can form, and if we find that there is a cycle, say if there is a link from T2 to T1 also, it means on particular data item, T1 has to be carry out its operation before operation done by T2. For some data item, it's reverse. If it is so, then that is not conflict serializable. There is a cycle. If we look into this one, here see, we don't have any cycle. So if there is no cycle in the precedence graph, so after forming the precedence graph, there will be a cycle detection technique. Order of n square, n is the number of nodes in the graph. So if there is no cycle, then this is conflict serializable. So this one is conflict serializable as there is no cycle. Now see, here what we can do, in the serial schedule, say T2 will be followed by T4, and T2, see, if we look into say, okay, we are starting from say T1, then T2 can be done before T3. After T3, T2 can be done because T3 precedes T2. So it can be then T1 followed by T3, then T2, right? After that, T4. So T1, T3, T2, T4, right? So T2 precedes this T4 and T3 precedes T1, T2. So ultimately from here we can come up to a serial schedule of this kind of thing, right? So now how will be ensuring, say I am writing a transaction, so how to ensure that the schedule it will be conflict serializable? So very popular kind of thing is log-based protocol. So whenever we have talked about Java, so there also we have said that for every object there will be some for shared data that will be part of, try to think about those thread kind of situation. That thread needs a data item, some code, that run method. And the data item, the simplest kind of strategy for that we talked about was the data which will be shared, we will be putting it in a different class. So whenever for that particular class, instance of that particular shared data, we'll be working with every object there is a lock. Similarly here also. So if we go by the philosophy in a very simple manner, see, with every data item in my database, a lock is associated. A transaction wants to work with a particular data item must acquire the lock in suitable mode. Now, suitable mode that depends on what I want to do on that particular data item. We are, if we look into Oracle offers a variety of lock mode, right? Here, to understand the philosophy, we'll be talking about two simple modes, exclusive and shared lock. See, if I want to modify a data item, modification in generic terms means I will be reading the current value in my program variable, then I will be modifying this, and that has to be sent to the database, right? So if I want to modify a data item, then the transaction must acquire the lock on the data item in exclusive mode. If it is so, I want to read only. I won't be modifying, the transaction will not modify the data item. Then it is sufficient to get the shared block. So depending on the requirement, the transaction will ask for the lock. If it can acquire the lock, then it will proceed. Otherwise, it will have to wait. Till it can get the lock, right? So that is the thing. Now there is a compatibility matrix like this that say a transaction has already been granted some kind of lock and another transaction has requested lock on the same data item in certain mode, whether they are compatible or not. In the simplest form, it is like this. Say, if we consider these are already granted, S stands for shared, X for exclusive lock. So if shared lock is granted on some data item, if we get another request for shared mode, that can be granted, but exclusive mode cannot be granted. Again, if exclusive mode on the data item has already been granted to certain data item, if it is already granted, then no other transaction can get hold of any kind of lock on that key. So exclusive lock granted to a particular data item to a transaction, if it is so, then no other transaction can get any kind of lock on that data item. If it is in the shared mode, lots of transactions can acquire shared lock on the same item, but nobody can get the exclusive lock in that case, right? So that is the compatibility matrix. So whenever a transaction is requesting for a particular type of lock on a data item, it will consult the compatibility matrix. If it is granted, if it is possible to grant, if it is compatible, then the transaction will proceed. Otherwise, it will have to wait. Now, whenever a transaction is over, say it commits or it rollbacks, then it will give up all the locks, right? Try to think out in Java, whenever or in OS also you have studied, say in OS we go for this wait signal kind of operation. So if we think about Java, that whenever a particular process, a thread is going into that synchronized method, once the execution is over, it will give up the lock. Or if it makes a call for, say, wait kind of thing, then also it gives up the lock, that kind of thing, right? So here also, whenever a transaction commits or rolls back, it will give up the lock. So other waiting threads, depending on the policy, scheduling policy, we'll acquire the lock on that particular data item and we'll proceed. Now, now we'll be looking into the schedule, we'll be putting the locks. Say, system is using, say, in generic form, as if using this kind of statement in the schedule, we are showing that if we write lock X within bracket some data item, then it means this particular transaction is requesting for exclusive lock, sorry, exclusive lock on this data item A, right? Whenever it is executing unlock A, so it is releasing the lock on data item A. Similarly, if we write lock SA, that means we are requesting, the transaction T2 is requesting for shared lock on the data item A, right? So this is the notation. Just in case I miss it later, in case of Oracle also, at the user level, we can, there is a lock command. But there, okay, just give me a reminder. I will say a couple of words on the locking issue of Oracle. Okay, that I will come later. So if we think about this kind of thing, now suppose this is a schedule. Say if it is like this, that transaction T1 is asking for exclusive lock on A, fine. So let us assume no other transaction is going on. This is the only schedule we are having. So transaction T1 will get the exclusive lock on A. It is reading, it is modifying, as it will be modifying. That's why it asks for the exclusive lock. So then it has written. After that, modification is over, at least from the transaction part. When it will be sent to the database, that depends on the policy of the concurrency control and say recovery module. So forget about that. So it releases the lock. So now say the schedule goes like this. This is the time. This is the timeline. So T2 goes for shared lock. Now it can get the shared lock. It wants only to read the value. So reads, then it releases the lock. Again it reads B, asking for the shared lock on B, reads and releases. It wants to show the total of A plus B. After that, transaction T1, it is now getting on exclusive lock on B, as the shared lock on B by T2 has been released by this unlock statement. Done. So it can get the exclusive lock on B. It is reading as if 100 rupees is being transferred from A to B. It writes, it releases. Right. So if we go by the locking principle, so this schedule is valid. Transaction T1 will be doing its job. T2 is also doing its job without waiting. But see, the problem of concurrency is not only the conflict serializability. We want to ensure there is no dirty read, no incorrect summary, no lost update kind of thing. See, in this particular example, if we consider we are transferring 100 rupees from A to B, then in my application, before the transaction, after the transaction, this A plus B, sum of the balance of account A and B remaining unchanged, will remain unchanged before, even if we do not execute the transaction T1. But here what it will show is it will show that it will have the incorrect summary problem. That means we are getting increased value for A, but B is not reduced. So as if we see, the summary shows that the sum of the balance of the two accounts has already been incremented by 100 rupees, although we have gone for transfer of money between the two. So what we try to conclude from this particular discussion is that simple use of the locks, mere use of the locks will not solve the problem, because it's not only the issue of serializability, but DBMS is one level higher. We want to get rid of the problems caused by the concurrent accesses, those lost update, incorrect summary, and dirty read, that kind of problem. So here, in this particular case, although we have applied the lock unlock in certain manner, but simple use of that is not going to ensure, it is ensuring serializability, but it doesn't ensure our incorrect summary problem. So that is the issue. So this is the conclusion. So mere use of locks is not the solution, right? Now, to solve the problem, if we focus on this part, if we want to solve the problem, we may think that we should not release the exclusive lock immediately when the job is over, because it has, as we have released this one, it has enabled T2 to access the value of A, right? So if we do not release this, say this unlock A is released, it is released say at later point, then when it is asking for shared lock, it will have to wait. So somebody may come up with a ready solution that, okay, instead of releasing the locks as and when the operation is over, will not go for that, right? Particularly, exclusive lock will retain this till the end of the transaction. Then, if we follow this, so the new schedule, it becomes like this. We have asked for the lock, exclusive lock on A, read it, modified this, written back, but unlock A, that statement has been deferred. We are not releasing. So now, whenever T2 asking for shared lock on A, it will have to wait, because another transaction, T1 in this particular case, is holding exclusive lock on A and they are not compatible. So it is waiting at this particular point of time. How long? Till lock on A is released. In between, we have read the value of, so as this is waiting here, so transaction T2 cannot proceed. So if the scheduler goes for transaction T1, it can get the exclusive lock on B. So it can read the value of B, modify these, writes back, then the locks are released. Only after this, so by this time, B has been modified. So only after that, the other transaction that wants to read the value of A and B, it can proceed. Now it can go for lock is A. So basically, the way the lock statement has been used and locks are released, effectively this schedule is converted into T1 followed by T2. So it gives us the idea that, okay, we particularly for the exclusive locks, we will retain the exclusive locks till the end of the transaction, so that somebody cannot get hold of this, and we can avoid not only incorrect summary but also the dirty deed kind of thing, right? So if we look into that, if we further modify these, so see here we are achieving the more undesirable problem of incorrect summary, but obviously concurrency will be to some extent that will be compromised, because see, we are forcing the things to make it a serial one, that T1 will be done, after that T2 will proceed. So as if this is forced into a serial schedule, T1 is followed by T2. So we are, in order to avoid the incorrect summary problem, we are compromising with the concurrency, right? So we can follow this kind of technique, but see, it doesn't mean that we can solve all the problems. See, we have further modified that particular schedule. See, this was the thing for T1, exclusive lock on A, it is getting, reading, modifying, writing it, but holding the exclusive lock. Then just look into T1, in between T2 will do, it is asking for exclusive lock on B, reads, writes, then it goes for releasing lock A and B. Okay, now see, we have changed the order. Earlier, we have gone for, in T2, we have gone for shared lock on A. Now see, it is asking for shared lock on B. That it can get because exclusive lock on A, that is with T1. T1 is yet to get the lock on B. So in the meantime, if T2 is scheduled, T2 can get the shared lock on B, it can read the value of B, then it is asking for shared lock on B, A. Now it cannot proceed because exclusive lock on A is with T1, so this request is not compatible. So it is waiting here. Now if scheduler comes to T1 at some point of time, T1 asks for exclusive lock on B. It cannot get the exclusive lock on B as shared lock on B is lying with T2. So now T2 is waiting for shared lock on A, T1 is waiting for exclusive lock on B. So see, here, although we have followed the strategy that, okay, we will retain the exclusive locks till the end. But see, we are facing a problem of deadlock here. T1 is waiting for the lock for B. That will be given up by T2 only if it completes. Again, T2 is waiting for shared lock on A. That can be obtained only T1 can proceed, goes to the completion. So T1 is waiting for the completion of T2, T2 is waiting for the completion of T1. So deadlock can occur. So here, I mean, if we are working with Oracle also, whatever policy Oracle follows, there also this kind of deadlock situation can occur. So what Oracle suggests is that whenever we are building the transactions, we may work with a common data set. Then we may follow certain order. Say, if we consider A and B are nothing but two, say, accounts, right? Say account number. If we can follow, well, while developing the application, that will be using the, if we are working with number of accounts, we will be using them in certain order. Say A and B, say account number A is smaller than account number B. If we consider, we will be using the accounts in the ascending order of their account number. And if the account number A is smaller than account number B, then the person who is designing this transaction, he will also use account number A earlier. So it will try to access lock, it will try to put the operation with the account A earlier in his or her transaction. So that means the previous one. Otherwise, see, there may be deadlock. So early release of locks may increase the concurrency at the cost of consistency. Right? That was the case. If we release the lock as and when we are done, we are in our example schedule 5, we have seen that we have come across incorrect summary problem. So consistency will be lost. And again, retaining of locks till the end, it maintains consistency, sacrificing the concurrency, but still that is acceptable. But mind it, moreover, there may be deadlock situation also. So we need some sort of locking protocol to decide when to go for lock, when to go for unlock. So again, before going for this, protocol, as we have talked about the precedence graph in case of that conflict serializable schedule through a sequence of non-conflicting swap. At that time, we have talked about the conflicting instructions. Similarly, here also, whenever we are working with the locks, here also we can form a precedence graph sort of things. Again, all the participating transactions in the schedule, there will be a node in the graph, right? And we can have a directed edge from Ti to Tj. It means that in our schedule, Ti holds a lock on certain data item in certain mode, say M1. Say Ti in the schedule, Ti at a moment is holding a lock on the data item A in certain mode, and at later point of time, Tj will request for a lock on the same data item in another mode, say M2, and they are not compatible. What does it mean? That means Ti is holding a lock on data item, and Tj will also ask for the lock on the same data item. The locking modes are not compatible. It means that in the equivalent serial schedule, Ti must be done before Tj. So earlier it was based on the it was based on the conflicting instructions. Now it is based on the compatibility of the locks. One particular transaction has to be done before another one in the equivalent serial schedule, provided it requests for a lock on the data item on a particular data item in certain mode, and on the same data item, the next transaction, it will be asking for the lock, and the corresponding modes are not compatible. So that is the thing. So in this manner, again, we can form a precedence graph. If there is a cycle, then we'll say, okay, this is not possible to go for serialization. So anyway, now if we go for, so if it is acyclic, if the graph, then we'll say, okay, this protocol is legal. So as per certain protocol, we'll form the schedule, then we can check it through the graph also. One such simple protocol is two-phase locking protocol. In this protocol, a transaction, it can remain in either in growing phase or in shrinking phase, right? As of now, if we draw the analogy, say, of these two terminology, say you are in growing phase, you have entire world to conquer. On the contrary, I am on my shrinking phase. I have lived the major part of my life. So now I'll have to make the planning to close down the activities, right? Similarly, for the transaction also, if it is in the growing phase, it will be asking for more data. So it is in the growing pattern. So whenever a transaction starts, it's in the growing phase. It may do more job. It may ask for more data. So in order to work with the data, it will be requiring the locks. A transaction can make request for locks only as long as it is in the growing phase. Once a transaction enters into the shrinking phase, it cannot make any request for any data item or any further lock. So when a transaction will enter into the shrinking phase, once the transaction has released the lock, then it enters into the shrinking phase. So whenever a transaction starts, automatically it is in growing phase. It can ask for the locks on the data item. It will do job on various data items. So it can go on asking for the locks on the data items. But once it has released a particular lock, so it has entered into the shrinking phase. Now it can only release the lock. It cannot ask for any new locks, right? So that is the idea. Now again, if we look our old examples, say this is our earlier schedule S5. See, a transaction T1, T2, so T1 starts, it is in now growing phase. So see, if we look into that, here we have put unlock. So that means the transaction has already entered into the shrinking phase. So at later, if it asks for this exclusive lock on B, so it is not a valid schedule under two-phase locking protocol, right? So forget about these other issues. So these under two-phase locking protocol, if a particular database management system is following a two-phase locking protocol, then obviously this schedule will not be accepted. So earlier we have seen this schedule resulted into incorrect summary. So this situation cannot arise under two-phase locking protocol. Now we modified this particular schedule to get rid of our incorrect summary problem. So now if we modify, if we consider that modified schedule, that S6 again, now how does it look like? It is asking for exclusive lock on A. It has read the value, modified, write A. Mind you, we retain the exclusive lock on A till the end, right? So it is not releasing. So T2 is asking for shared lock on A, right? But it cannot get it. It will have to wait. So this transaction, this process is waiting. So at some point of time, this process T1 will be scheduled. So it will be asking, as it has not released the lock, so it can ask for new lock. It is still in the growing phase. So it can get the lock on B. It will carry out the job. At this point, it enters into our shrinking phase. So earliest at this point of time, this T2, if it is scheduled, it can get the lock, shared lock on data item. So see, as intuitively you modified the transaction, I mean that schedule S5, like this, by retaining the locks till the end, that thing is valid under two-phase locking protocol. So if to the system, if this that follows two-phase locking protocol, if this schedule is given, this will be accepted. Mind you, the schedule that resulted into deadlock, that will also granted under two-phase locking protocol. So here, okay, transaction T1 not releasing the lock on exclusive lock on A, so it is still in growing phase. So it can later ask for exclusive lock on B. But in the meantime, T2 asking for shared lock on B, it will be granted, it is waiting. So see, under two-phase locking protocol, it is ensured that there will be no incorrect summary, that kind of problem, but still deadlock can occur. So obviously, if the database management system is following a two-phase locking protocol, then simultaneously it will have to maintain, it will have to run the deadlock detection algorithm to check whether the system, or it can go for deadlock avoidance. Possibly if it is following two-phase locking protocol, then it will have to go for deadlock detection algorithm to check whether deadlock has occurred or not. In that case, it will have to forcibly terminate either maybe that all the participating, or at least some of the participating transactions, and that will invite the recovery policy, as we discussed about the cases of failures that may ask for the recovery, right? So that is the two-phase locking protocol. We have some variants of, of this two-phase locking protocol, or other lock-based protocols also, to focus on some other issues. So that you may study of your own. Just to give up the idea, I have summarized the two-phase locking protocol. Now, more serious problem may come up. Say, if we look into this schedule, say transaction T1, it is reading the value of X, modifying this. That is, I mean, this is the case of lost update kind of thing. In the meantime, transaction T2 is reading the value of X. It will also modify. Forget about the locking and all those things right now. Right? And say, then transaction T1 goes for write X, it will go for read Y. Then say transaction T2 goes for write X. Then what will happen? As we have seen in case of lost update problem, the update that has been made by transaction T1, that will be lost, because both of them have read the old value. Both the transactions have read the old value of X, and the one which is performing the write operation, the updation of that one will be there, the other one will be lost, right? So that is the case. Let us see whether under two-phase locking protocol, whether it can happen or not. So if we put it this way, say T1, T2, so T1 wants to modify. So I mean, if we try to put here, it wants to go for read X. As it will be modifying, it will require exclusive lock on X. Similarly, T2 also will require this one. So now if we put it under two-phase locking protocol, so T1, it will go for asking for exclusive lock, it will be granted, read X. Now see, T2 is waiting here, right? T2 is waiting here, it cannot get the exclusive lock on X. So that means our two-phase locking protocol, although this is little bit stringent compared to other kind of techniques, but still, see, it's not only that, it ensures that there will be no incorrect summary problem, but it also ensures that there will be no lost update problem. See what happened, both was reading the old value and both will be modifying this. So as both are reading the old value, so one of the changes made by one of the transactions will finally remain. Now as both will be asking for exclusive lock, only one will be granted, so other one will have to wait till it is released in the shrinking phase. So that way, two-phase locking protocol also ensures that there will be no lost update problem. Fine. So that is also addressed. But mind it, deadlock can occur. Now we will follow timestamp based protocol. So this is also, I mean Oracle mostly follows log based protocol, and in Oracle there are lots of varieties, right? It goes for row level. It goes for row level logs, and that is automatic. As user, we are doing nothing. System will do automatically, and there are wide variety of locking mechanism: shared, exclusive, row share exclusive, shared row exclusive. I also do not remember nowadays all those kind of varieties. But the basic thing is that for simple reading a data item, it doesn't require, in Oracle, it doesn't require any lock. Every so, I'll be modifying the data. Say it finds that I have written update some statement, said this equals to that, where some conditions. Then it will check what are the rows are going to be affected. It will try to acquire exclusive lock on those rows. So parallelly, if some other transaction is working with some other set of rows, they will not wait for each other. One transaction will be getting the exclusive lock on the set one to update or modify that kind of activities. The another transactions that is working with a different set, say set 2, where the intersection is null, exclusive lock on the set 2. So that way it tries to increase the concurrency. But if there is some intersection, then obviously it will have to wait. It cannot get the locks. But in case of Oracle also, deadlock can occur. So while developing the application, if we can make a protocol of our own that we will be using the data in a particular order, as I have said, in the ascending order of the account number in my set of rows. That kind of policy, if we can formulate, okay, then in most of the cases or in some of the cases, we can avoid the deadlock. In case of Oracle, to the end user, there is a lock command, but using that, I can go for lock at the table level. So I can acquire exclusive lock on the table. Suppose as administrator or as owner of the object, I am going for, say, changing the schema, then I can go for having exclusive lock on the table so that nobody else can carry out any operation on that particular table. So we are not given row level locking facility to us, and normally whenever we are working in commercial database management system like Oracle, we are not bothered about issuing the locking commands until and unless very specialized, very crucial kind of thing. Find it, Oracle has given the lock command to the end user to apply lock on the objects owned by the user, but at the table level, not at the row level. So for the update, delete, insert, that kind of or select kind of statement, Oracle will be doing the things of its own. And in case of concurrent activity in Oracle, I cannot see the uncommitted changes made by others, made by the other transactions. Uncommitted changes made in the same transactions that are visible to the transaction, that obvious, but uncommitted changes made by the other transactions will not be communicated to other transactions, right? So anyway, that is specific to Oracle. So timestamp, that is again another interesting concept. It is so that for every data item in log-based protocol, a lock was associated. Here, in timestamp-based protocol, for every data item, first of all, every transaction will have a timestamp. Say transaction TI, TJ. So when you say TS, TI, it means timestamp of TI, timestamp of TJ. It may be depending on, say, starting time. The transaction which one has started earlier will have lower timestamp. So if we say that TI has entered into the system earlier, it has started earlier, then timestamp of TI will be less than timestamp of TJ. So it can be assigned using the system clock, or we can keep a counter. Whenever a new transaction comes, counter initially 0, it will be incremented, and that value will be the timestamp of the incoming transaction. So the one which is coming later will have the higher value, right? So that way, timestamp can be given to the transaction. Now here, serializability, that is based on the timestamp value. So the one which has started earlier, that means with lower timestamp value, as if in the equivalent serial schedule, that will come before the other one. That is the basic principle. So as I started saying, then I went back that for every data item X, there are two timestamps, just like the lock with every data item in log-based protocol. Here for every data item, there are two timestamps. One is the write timestamp, another is the read timestamp. Write timestamp means it stores the transaction which has performed the write operation, timestamp of the transaction that has performed last write operation on the data item, right? And RTS is similar. It is the most recent transaction that has carried out the read operation on the data item. Right? Now, see how the protocol works, how the timestamp ordering it will be working. Suppose a transaction TI, it has issued the read operation, whether it will be allowed or not. See, it is done as follows. Say, if the timestamp of TI is less than right timestamp of X, then reject the read X and roll back TI. What is the physical significance? That is, as if some transaction with higher right timestamp has carried out some write operation on X. That means somebody who has come later has already done some operation on X, right? And this transaction, it has started earlier, as if it was supposed to read the old value. As if, think about a situation, as if I am the transaction TI and say, I will be saying what is the score, then say this is our controller, then controller will do some, say, incremental operation on the score, as if he will be giving a grace of 5, COVID grace. Now, before I say, I have said you that this is the value, it has already done some activity. Physically, it is interpreted as the transaction which has started earlier, lower timestamp. It was supposed to read a value on X, the old value on X, which have been already modified by some transaction started later. So as if this earlier transaction was supposed to read the old value, the earlier value of X, which now doesn't exist. So that's why reject read X, roll back the transaction. So this transaction itself is cancelled. So if you really need to know the value of X, even if it is modified, then it will be started again. You will be carrying out the operation once again. Now it will get higher timestamp value. So now this time will be allowed. Right? Otherwise, it assumes the earlier transaction was supposed to read the earlier value, which is no longer present. So if the timestamp of the transaction carrying out asking for the read operation is smaller than the right timestamp of the data item, then it will not be allowed. So in the other words, so if timestamp of TI is greater than equals to this, then it will be allowed, and it will be, so RTS as timestamp of TI, I mean TSTI is greater, I mean if it is allowed to read, then RTS of X also has to be changed. So RTS of X, the read timestamp of X, it will be maximum of timestamp of TI which is performing the read operation and present RTS of X. Why it is so? Why it is max of these two? Say timestamp of TSX, say right timestamp, say this is say 500. Say timestamp of TI say 100, there is say another transaction that is 200. It may so happen that transaction with timestamp 200 that also has read the value of X. So for that transaction also 200 is less than the right timestamp, that is 500. So that was allowed. So already RTS of X is 200. Now this transaction with timestamp 100, see, it is not checked with the RTS. While I am reading a transaction which has started later to me, that also can already perform read operation, and that also can modify the RTX. So that's why I cannot blindly write that RTS of X will be equals to RTS of X. I mean, I cannot write simply this will be equals to timestamp of TI, because there may be some other transaction that has started after TI and has carried out the read operation on X. So that's why while after a read X operation, we'll go for setting the read timestamp of X, we'll have to go for this operation, right? So that is how the read operation, whenever a read operation is issued by a transaction, how it is evaluated. Now, if we follow the same principle, say whenever a transaction is trying to go for write operation, first thing, if the timestamp of the particular requesting transaction is less than RTS X, physically what does it mean? As if some transaction that has started later has already read the value. As if we think about the chronological manner, so nowadays in our country it is very important to understand the chronology. So if we go for the understanding the chronology, as if transaction TI, it was supposed to write a value. So later people will be going for accessing the value. Now if I find that some transaction that has started later was already satisfied, already read the old value, then we'll say that it is useless, you will be modifying these, because people who have come later have already worked with that particular old value. So it will not be allowed. So same philosophy. In case of read operation, that if some transaction started later has modified the value, you were supposed to read the old value, not available, I will not allow you. Same thing, same philosophy. People who have started later have already read the value. So I'm not going to allow you to modify these again. So reject and roll back. And again, in case of write operation, we'll have to check with both the timestamp. If we see timestamp of TI is less than the write timestamp of the data item, that means some transaction that has started later have modified the value. Again, if we go by the chronology, this has started earlier, as if as per the timing chronology, it was supposed to modify the value of X. After that, the transaction which has already carried out, it would have modified, and its value will be the one with the maximum timestamp, that value will be retained. But if we find that some transaction that has started later has modified the value, and the system must say that its value has to be retained, then this intermediate operation, as per the chronology, it will not be allowed. So this will be rejected. So write operation will be rejected only if no transaction started later have neither read nor carried out write operation on the data item. Now in this case, one can go for writing, setting that WTS, otherwise it will be allowed. Once this is allowed, okay, you can go for writing, write timestamp of X will be timestamp of TY. But to maintain the parity, I have followed the same thing, max function here. Max of the current write timestamp and timestamp of TI. But okay, as per the logic, you can understand here always it will be timestamp of TI, because otherwise the write operation will not be allowed. Now see, timestamp based ordering, it ensures conflict serializability, right? Here also there won't be any lost update problem, there won't be any incorrect summary problem. Here the ordering is based on the timestamp, right? And important to note that as in case in this protocol, there is no issue of waiting. Try to remember what you have studied in operating system. There are four conditions must simultaneously be present for a deadlock. One of them is wait. If there is no wait, so there will be no issue of deadlock. So timestamp ordering protocol is deadlock free. So that is a difference with the log-based protocol. Now, with this idea, will of concurrency control, will look into a few aspects of recovery once again. Now see, if we keep in our mind this concurrent situation, issue of cascading rollback may come up. Let us look into a schedule like this. Say transaction T1 is reading the value of X, say write X, read Y, read Z. See, it is doing like this. You follow the two-phase locking protocol, no issue. So it will go for exclusive lock on X, then say shared lock on Y, shared lock on Z. Maybe that it is going for say unlock exclusive lock on A, maybe like that. So it can go for shared lock on A, I mean exclusive lock on A, T2, and say it wants to work only with T2 say. So after this, it may go for undoing the unlock. So it can go for having the lock on X, if this is the timing order. So T1 is modified the value of X. After that, T2 is reading the modified value of X and doing further modification, and say T3 is modifying the value of X. Now suppose these are partial things. Say at later point of time, say T1 fails, right? T1 fails. So it will, or say T1 rolls back. If it fails or if it rolls back, then it cancels whatever it has done. Then to ensure the consistency, T2 also has to be cancelled because it has worked with the modified value of X done by the T1. That modification is getting cancelled. So T2 also has to be cancelled. Again, T3 has worked with the modified value of T2. So T3 has also to be cancelled. So there is a one rollback is leading to a sequence of rollback. This is known as cascading rollback. So in a concurrent environment, for recovery from a transaction failure, it may be necessary to roll back number of other transactions. When it occurs, whenever a data modified by one transaction is used by others and any one of the preceding transaction fails, that leads to the subsequent transactions that have worked with the data item modified by the failed transaction. Now see, this is an overhead. This can occur in case of two-phase locking protocol. This is obviously an overhead. Say we'll have to go for undoing lots of activity, right? So we want to, whenever we are going for some locking protocol or concurrency protocol, so we'll have to ensure that cascading rollback can be avoided. Still, somebody may say that, okay, the previous example that we have put into the two-phase locking protocol scheme, exclusive lock on X, read, write, again exclusive lock on Y, it reads, say exclusive lock on Z, reads Z, say it has released the exclusive lock on X. So now transaction T2 can get exclusive lock on X, it has read, writes, it enters into shrinking phase. So it can get the exclusive lock on X. So these are partial. Say after that, say if T1 fails, so it will lead to lead to cascading rollback. But see, this schedule is valid under two-phase locking protocol. So in the existing form of two-phase locking protocol, it is possible to have the cascading rollback. So if we want to avoid this, it has to be modified, right? In case of timestamp based protocol, see, there also cascading rollback can occur. See, as T1 has started earlier, timestamp of T1 is smaller than timestamp of T2. Again, timestamp of T2 is smaller than timestamp of T3. Now, just forget about the locking thing. That lock statement will not be there in case of timestamp based protocol. So, just get rid of this. So, read X. T1 is asking for read X. So, it will be allowed, write X, it will be allowed. After that, if it goes for read X, so it will check what is the right timestamp. Right timestamp, possibly as per this schedule, it will have the timestamp of T1. So timestamp of T2 is higher. So these read operations will be allowed. Similarly, this thing will be allowed. So if we minutely follow based on the timestamp ordering protocol, here the cascading rollback can occur. So both of them are to be modified. But see, cascading rollback, still through rollback, we can handle the situation, we can maintain the consistency. Only thing is that it is costly. We'll have to undo the effect of so many things, right? So that's why this is not desirable. But more serious problem is that at all it will be recoverable. Suppose this is the situation. Say, if I put it under two-phase locking protocol, yes, it's there. Say T1 asking for exclusive lock on X, reading the value of X, modifying the value of X, then asking for the exclusive lock on X, it has released the exclusive lock on X, right? So it has entered into the shrinking phase. Now T2 is asking for exclusive lock on X, so it can get, right? T2 is reading, writing, unlock. Say T2 is over, and this after that T1 goes for write Y, unlock Y. Say at this stage transaction T1 fails, and say before that transaction T2 has committed. Now see what is the situation. This was valid under two-phase locking protocol. Now, how to go for recovery? Contradictory situation. T1 has failed. So, we'll have to cancel the effect of X. So, the changes made by transaction T1, that has been used by, consumed by T2, and that transaction has committed. So as this particular transaction has committed, then we'll have to ensure the durability. So basically, under two-phase locking protocol, in the concurrent environment, the schedule may not be recoverable. So two-phase lock, so far the way we have studied the two-phase locking protocol, it doesn't ensure recoverability. Cascading rollback, okay, that is not desirable, but still we can put the database into consistent form through some lots of cancellation effect or undoing operation. But if this is the situation, this particular schedule, it shows that even the recoverability, that is also not guaranteed. So it needs some modification. What modification now say we are putting? Earlier what we have done this unlock operation here. We have entered into the shrinking phase. Now strictly we are saying that exclusive locks are to be retained till the end point. then we cannot keep it unlock X here. We'll have to hold this one till the end point, right? So if we hold this till the end point, right, then this transaction T2, it cannot get the value of this particular value of, cannot get the exclusive lock on X. So it will have to wait. So again, earlier two-phase locking protocol said that, okay, once you give up the lock, you cannot ask for the new lock. So following that one, we have seen, okay, we can still have two-phase locking protocol, maintaining the two-phase locking protocol. We can have the schedule, but that can lead to non-recoverable schedule. But here, whenever we are saying that, okay, we'll have to retain the exclusive locks, because that means these data have been modified. So it's not that I'll be releasing the locks at the very beginning of the shrinking phase. Rather, at the end only we'll be releasing that. It ensures that cascading rollback is avoided and recoverability is also ensured. So that means in the two-phase locking protocol, in the concurrent environment, if we want to ensure that there will be no cascading rollback, and there must be, it must ensure recoverability, then we'll have to retain all the exclusive locks till the end, not at the beginning or initial part of the shrinking phase. Only at the end, towards the end of the shrinking phase, we can give up the exclusive locks. Shared locks we may give up. Right? So this is one change. And in case of timestamp ordering protocol, that can also lead to this cascading rollback, and that also doesn't ensure recoverability. So we'll have to go for some modification, right? So in this case, so what is the modification? For every transaction, we associate a commit bit. We associate a commit bit whenever the transaction, not only a timestamp but also a commit bit. Say whenever the transaction commits, it will be set to true, denoting that particular transaction has committed. Initially, it is false. So whenever a transaction starts, a timestamp is given to it, and again, a commit bit is created for that particular one, is assigned for that particular transaction, and it is initially false. Now, whenever a transaction wants to perform the read operation, right? This was the earlier condition, that if we see the timestamp of the transaction, if it is smaller than the write timestamp of the data item, that is somebody that has started later, have modified the value. So I was supposed to read the old version, the earlier value. So it will be rejected and rolled back. This operation will not be allowed, transaction will be rolled back. In the earlier version, otherwise it was allowed. Now see what it does. If timestamp T is greater than, so this is the otherwise. That is, the timestamp of the transaction is greater than equals to the write timestamp X. Then, instead of blindly allowing the write operation, it checks if the commit bit of the last transaction that has carried out write X is true, then only the read operation will be allowed. Otherwise, it will have to wait. How long? Till the commit bit of the corresponding transaction that has carried out the last write operation is true. So what are the changes? Earlier in the timestamp ordering protocol, there was no wait clause. Now waiting state has been introduced. Earlier it has checked that whenever a transaction is trying to read, if the timestamp is smaller than the right timestamp of the data item, so some transaction that has started later has modified the value. So as if I was supposed to read the old value, which is no longer available, so I must not be allowed, and so rejected the statement, it is rolled back. Fine. Earlier, otherwise it was allowed, and accordingly RTS of the data item will be changed. Now what does it say? That if the, so otherwise means if the timestamp of the transaction asking for the read operation is greater than equals to the right timestamp of the X. Now it is checking the transaction which has carried out the right operation. What is the status of that transaction? Has it committed? If it is committed, then only the read operation is allowed and RTS is set. So uncommitted change is not being communicated. So now the transaction will be waiting. And note, a particular transaction T, it is waiting when it is greater than equals to WTS X. For some transaction, for the completion of the some transaction that has started later. This is very important. Try to understand. See, these allow or wait, this situation will arise only for this case. A transaction T is waiting for the completion of a transaction that has carried out the right operation on the data item, and that timestamp of that particular transaction is higher than the timestamp of tree. That means I can wait for the completion of a transaction that has started later. So I will not wait for any transaction that has started earlier. So this is clear. So if transaction T is waiting, that means it is waiting for a transaction, say T dash, that has started earlier. Started later. Say T dash has carried out right operation. So it is having higher timestamp. So T is waiting. So if we look for a dependency kind of thing, T is waiting for the completion of T dash, which has started earlier. So there is no possibility that T dash will be waiting for T. A transaction that has started later will not be waiting for a transaction that has started earlier. That will never occur. So it means there is an ordered waiting. There is no cyclic waiting kind of case will occur. So that's why, although we have introduced in the modified timestamp ordering protocol, although a wait kind of situation has been introduced, but a transaction can wait for another transaction. Let me make a correction possibly. TST is greater than equals to WTS X. Sorry. So basically timestamp of T, sorry, I have done a mistake. Timestamp of T is higher than the transaction that has done the right operation. So basically a transaction can wait for a transaction that has started earlier. Reverse case will not occur. Timestamp T will go for waiting state for completion of whom? For a transaction that has carried out right operation, and timestamp of T is higher. So basically a transaction T is waiting for the completion can wait for another transaction with lower timestamp. Reverse will not occur. So there is no cyclic wait. So that's why this modified protocol is still deadlock free. So the modified two-phase locking protocol retain exclusive locks till the end. There deadlock can occur, but that is also free from cascading rollback, and the recoverability ensures recoverability. Here also the modified timestamp protocol, this is also ensuring avoiding cascading rollback and ensures recovery issue, and furthermore it is free from deadlock. Right, now simply we'll go for the last thing. I will take hardly 10 minutes more. Say log based recovery we have talked about, and we have talked about the checkpoint also. Try to remember that we went for the system will be carried out the checkpoint operation periodically. What it will do at that time, all the modified data buffers will be written into the data blocks. As there is write-ahead logging, before that all the log records will be put into the log file. Then data blocks will be written to the data buffers will be written to the data blocks in the disk. After that, it will make an entry that checkpoint operation has been carried out at this particular point. Whenever we mentioned that all the time scanning the whole log file, that is time consuming, and most of the times the redo operations that will be carrying out, those are redundant, right? So to get rid of those, system introduces, in case of log based recovery, consider the checkpoint aspects. Earlier we considered that there is no concurrency was not considered, so we thought that okay, at the time of checkpoint operation only one transaction may remain in active state. So that way we define as if that whenever we will be carrying out the redo operation, recovery operation, we will be considering the part from the most recent checkpoint to the end, rather moving in the backward direction. Not only the last checkpoint, beyond the last checkpoint till the most recent TI start kind of thing, as if that particular transaction was active at the time of our checkpoint operation, right? But now, as we understand the concurrent kind of scenario, whenever we are carrying out the checkpoint operation, it's not that only one transaction is in active state. So how shall we understand? Try to understand, realize the difference. Earlier it was so that at most one transaction may remain in active state at the time of checkpoint. So we went beyond the most recent checkpoint record till in the backward direction, till we encounter the first TI start, because in the worst case that was in active state. But here we don't know. There may be 2, there may be 3, there may be 4. So from the most recent checkpoint operation in reverse direction, how many TI start we will consider? So that's why whenever we are considering this concurrent environment, along with this checkpoint record, it will put a list of the active transactions, maybe the ID of the transactions which are active at the point of checkpoint operation. So that is one fundamental difference. Now how we will carry out the recovery? So we'll have to prepare the redo list and undo list, just as we did earlier. So how we carried out the list preparation? Scan the log file from the end, move in the backward direction till checkpoint L. The most recent checkpoint record is reached. So if we find an entry TI star, TI commits, then we'll put this transaction into the redo list. Initially they are empty, and whenever we find TI star, and if this transaction is not in redo list, as we are moving in the reverse direction, so for a committed transaction, a commit entry will be encountered before a start entry. So whenever we are encountering a start entry, if it was actually committed, then already it is in the redo list. Otherwise, it will be put into undo list. Now, so this way we have reached up to the checkpoint L, the most recent checkpoint record. Now, for every transaction TI in this list, that means the transactions which were active at the time of checkpoint operation, now we are looking that if those transactions have already committed, then obviously already we have encountered a commit entry during the process of traversal, right? So if it is not in redo list, then we'll have to understand that particular transaction was actually failed. So we'll put those into the undo list, right? So now the redo list and undo list, that is complete. See, earlier we considered up to this, now this is the additional thing. Okay, so once this is done, then we'll what portion of the log file we'll consider. Earlier it was from the end to the most recent checkpoint operation, beyond that till the TI first, most recent TI first, right? Now, see, during the process of creating this list, we have moved in the backward direction, and we are now at the checkpoint, most recent checkpoint entries. Now, move further beyond the checkpoint L in backward direction till TI start for all the TI in the list is reached. That means beyond the most recent checkpoint reached, we'll have to consider all the corresponding log entries of the transactions which were active at the time of checkpoint operation. So beyond the checkpoint record, we'll have to move in the backward direction till we find TI start for all the transactions that are in the checkpoint list, right? So this is the portion of the log file that now we will consider. So once we go to such point, that will say that will be the beginning of the part of the log file that have to be considered. So now we'll be performing the undo operation in the forward direction. Sorry, we'll be carrying out the undo operation in the backward direction from the end of the file, right? And we'll be moving up in the backward direction. So how long we'll carry out? So mind it, we'll be starting from the end of the log file. It was saying earlier in the backward direction, we'll be moving in the backward direction beyond most recent checkpoint L till TI start for all TI belonging to L is reached. That we have talked about earlier. So that is the part of the log file we are now considering. Now try to understand. Now this is very important. Why we are carrying out this undo operation by moving in the reverse direction. Suppose two transactions that were active, right? Say transaction TI and TJ say TI have changed the value of X from 10 to 20, and later TJ has changed the value from 20 to 30. So in the log file, if we move in the forward direction, then we would have found that TI has old value 10 for data item X, old value 10, new value 20. At later point of time, we will find TJ old value X, for X, old value is 20 because it has worked with the modified value of TI, value modified by TI. TI earlier has modified this from 10 to 20. TJ now making this from 20 to say 30. Now, if we carry out the undo operation in the forward direction, then you will be using the entry of TI first. It says that old value is 10. So you will be doing the undo operation making this 10. Later you will find that TJ as old value is 20. So you will be carrying out the undo operation making this 20, and your cancellation is wrong because TJ changed it later looking into the value given by TI, right? Looking into the value modified by TI. Actually TI, TJ both have to be rolled back. Effect of both have to be cancelled. So TI cancel means TI change the value from 10 to 20, then only TJ make it 20 to 30. So if TI, so issue of cascading rollback. So it has to be done in the reverse order. First of all, we take the entry of TJ. So TJ says old value is 20, so I'll make it 20. Then I'll go for the entry of TI. It says old value is 10. Then finally I'll be making it 10. So that's why rollback is done in reverse order. In say non-concurrent environment earlier, we could have done it in reverse order, in forward order. It doesn't say anything much, but to maintain the parity of the algorithm. So I talked about in the reverse direction that time. In reality, it has to be in the reverse direction as this is a concurrent environment. Database applications are in concurrent environment. So that's why it is in reverse direction. So anyway, so once the undo operation is done, starting from the end, moving in the backward direction, how long? Go beyond the most recent checkpoint. How long you will go beyond? Till I find TI starts corresponding to every transaction in the active list at the time of checkpoint, right? So while moving this way, whenever we find a transaction is in undo list, then use the old value. Obviously, the issue of undoing will arise only if this is immediate database modification or if it is still approach. If it is not a still approach, no still approach or deferred database modification, then there is no issue of undoing. But we know the pros and cons of those things. So after carrying out the cancellation effect, we are waiting to which point? We are waiting to a particular entry beyond the checkpoint L, covering all the TI star. So from that point onwards, we will be carrying out the redo operation in the forward direction till the end. Now this time, whenever we have a log entry of modification entries like transaction search, modified search data item from this value to that value, if that particular transaction is present in the redo list, then modify the data item in the database using the new value. So this way we will be doing the carrying out the operation, right? So in case of commercial database, these recovery aspects, locking and unlocking, all are being automatically handled by database management system. So we have talked about so far some background information, the policies and principles, how the things are basically implemented by the database management system. But whenever we are using some commercial database management system as a replacement to the file processing system, we are free from taking all the troubles. The DBMS itself is taking the measures to ensure recovery aspects and the concurrency aspects. So the points that we discussed in the very first class, that why shall we go for DBMS, possibly now we have covered the aspects. Okay, so that's all from my side.